Welcome to this presentation. My name is Srikar. I'm a manager at Machine Learning and Data Analytics at Active Safety, Volvo Cars. I'm going to talk about applied machine learning in the case of Autonomous Drive. Autonomous Drive is like a new exciting field. It is giving a lot of new opportunities in the areas of transportation system, city planning, as well as active safety. At Volvo Cars, this is a highly prioritized task, and we are making our efforts steps towards the future mobility solutions. But when it comes to safety, Volvo Cars is about safety, has always been about safety, and will always be safety. And these are the three main pillars for Volvo Cars Autonomous Drive that makes the steps towards the commercial autonomous vehicle. One is the Drive Me project. That is a collaboration with the cities in Sweden and the road authorities. And we have the joint venture with Veoneer and Autoliv called Zenuity, a company that is specialized in making autonomous software for automation in vehicles. And we have a project with Uber, where we are making a redundant base vehicle that is ready to take challenge to put self-driving car solution. At Volvo Cars, we believe autonomous drive is an enabler for future mobility. We are in actually a transition phase. Traditionally, we have been a car manufacturer. Now we are making steps towards future mobility solutions. And we believe this is one of the steps. So, sorry. What we believe is we would like to give a freedom to move in a sustainable, personalized, and in a safe manner. Not only delivering a premium car, we would like to be part of the society that fundamentally changing the scenario rather than just delivering a premium car. So people are talking about autonomous cars, but maybe some of them may not know, but there are different levels in an autonomous car. One is from level 0 to level 5. Level 0 is basically there is no automation. In level 1 and level 2, we have some kind of automation where we get this adaptive cruise control, blind spot warning, and lane departure warning, and lane keep assist. The tricky part would be the level 3, where the driver is still responsible, but you can get some kind of conditional automation, which means that the car can give back the control to the driver at any moment. So the driver has to take back and drive the car. So at Volvo Cars, we are not developing any car in this category. We are jumping from level 2 to level 4, which is 4 and 5. I mean, right now we are concentrating level 4, which is fully autonomous. But the thing is, it will do the safety critical driving functions for a short trip, for example, a highway pilot. But it doesn't have the capability to able to drive in each and every possible scenarios. Whereas in level 5, it is as good as like a human driver. So what makes the autonomous cars work? So like for us, we have sensory organs like eyes, ears, nose to smell, and hands to touch. Similarly, like a self-driving car will have sensors so that it can do the perception and make an actions based on that. The cameras will help to detect the objects nearby and also helps you to track the lane markings and helps to predict or identify the pedestrians and any obstacle that might come in front of the vehicle. Whereas the radar will give you like a 360-degree view of the surroundings and helps you to change the lane by tracking the vehicles that is coming from behind. And the sensor here would mean that ultrasonics that is able to detect the objects with very low speed. We have then a laser or Lidar with a multi-beam laser, which gives like exceptional vision. And then it also has a long range up to like 150 meters, so you can see far ahead and then able to distinguish the object. And it gives like a plenty of time to warn the driver. And after that, we also have like a highly detailed 3D map along with high precision GPS. This kind of work are kind of integrated together so that the car knows exactly where it is and what are our surroundings, so that it will try to find a way that is most efficient and safe. So what are the other enablers? We have seen the car sensors and high position GPS. So connectivity is also one of the important aspects. So the car not only just connected to the cloud, it should connect to the other cars and to the infrastructure and also to the humans. By connecting to the other cars, you get like information such as like traffic conjunctions, other obstacles that may appear maybe later a point of time in front of your car. So you can get transmitted that information to your car. And by connected to the infrastructure, you know about the environment, like the buildings, traffic signals, traffic posts, lights, and so on and so forth. And of course, machine learning algorithms. So machine learning could be used in autonomous drive in various cases. So in case of sensor fusion, where we fuse information from different sensors, you could use like a clustering and segmentation. And for road, you can track the ego motion, and you could use some sort of image processing to classify the road in front of the vehicle as, is it like a slow, slush, icy, asphalt, so on and so forth, because in the case of autonomous drive, the car should be disengaged if it's like a slippery road. So we should know what is the road condition as well. And you could use some kind of technique called simultaneous localization and mapping to localize yourself and our surroundings. We use motion planning and control for trajectory planning. And people use like supervised learning and reinforcement learning in the case of control strategy. And finally, the detection and classification of objects in the case of situational awareness. So my rest of the talk will be mainly concentrated on this situational awareness. So I'll go deep dive into the latest state-of-the-art methods that are available and do a comparison for that. So maybe some of the people know this, but yeah, object detection is one case of situational awareness, but what is object detection? So first, maybe moving towards an object detection, what is classification? In the case of image classification, we have an image, we have to just classify. If it contains a cat, you have to say cat or dog. And the next is like classification plus localization, where we not only should detect it's a cat, but should be able to localize where exactly the cat is inside this image. And the object detection is complicated compared to this, so you have multiple objects inside an image, you should be able to detect them, classify them, and then able to localize. And finally, instant segmentation, where you have to be able to classify each pixels inside this image. So basically, you can divide the object detection algorithms into two categories. The topmost is the traditional way of doing object detection, where initially you propose some kind of boxes onto the image, and you find out whether there exists any object in any of these boxes. Whereas the second category treats this problem as like a regression or a classification problem, so it has a unified model to finally take an image and then say whether there exists an object and what is the location of that an object. So we'll go through each of these methods. So first, the RCNN is called region-based convolutional neural network. So RCNN is actually kind of the algorithm that really kicked off the deep learning and object detection. It is in, I think it's 2000, they have the archive paper in 2013, but then it was in 2014. So it does what you intuitively do as well. Suppose you are given actually an image, so you throw some kind of bounding boxes where you think that there is an object, and then you classify whether there exists an object or not. So this is exactly the RCN concept is. So you have an image, so it scans an image and then finds possible or probable objects by using an algorithm called selective search. So you have like 2,000 of these proposals for an image. So once you find these proposals, you truncate them and make into like a standard size, and then you basically send it to a modified version of AlexNet. And once the output of the CNN then is given to a SVM classifier to detect what kind of class is that, and then the bounding box regressor to actually tighten the linear regressor to tighten the bounding boxes. It was first of the method which actually gave pretty good performance, like 53.3 mean average precision. That was like a 30% improvement before the state of the art. One problem here is like that you actually find this proposal based on an external algorithm, so it takes some time because you need to do these 2,000 proposals. And one more aspect is, at the end of this architecture, there is fully connected layers, which means that all of these images has to be a standard size. It doesn't work with any arbitrary size. Because we have multiple training objectives here, a CNN and a classifier and a bounding box regressor, so the training is quite slow. Initially, it used to take like 84 hours during that time. And it's also expensive in space. It used to take a lot of space as well. And another disadvantage here is, because you try to propose many of these regions, you do the same thing again and again. So it's like a lot of redundancy is there. And that time the detection is actually, it used to take 47 seconds to classify objects in an image. That's quite a lot. So what the people did later, that to remove some of these drawbacks from the RCNN, they proposed called SSP-net, wherein they introduced a new concept called spatial pyramid pooling layer. So you might think, why we need to have these 2,000 proposals and you have to run these 2,000 CNNs on each of these proposals? Why can't you actually have just one CNN that extracts all the features, and then you find a way to actually come back to the proposals? This is exactly what SSP-net does. So before proposing these region proposals, it actually extracts the feature from the image using just one CNN. And the other problem I was saying is like, because in RCNN, once you have the proposals, you need to truncate into standard size because of this existence of fully connected layers. So they solve this problem by means of introduction of this spatial pyramid pooling layer. So they introduced this at the end of the convolution layer in between and the fully connected layers. The goal is to take any arbitrary size and then make it into fixed size so that it goes to the fully connected layers. Because I mean, in a sliding window in a convolution layer can work with any size image, but the fully connected layers by default has a fixed size. So they solve by using this spatial pyramid pooling layer. So in this image, the black ones are the feature maps. So they propose a pyramid of pooling layers where it exactly does a sliding window of these feature maps and extracts the features so that you have a standard size. Still, it has ad hoc training because we have still SVM and then CNN is different and then also the bounding box. So only thing it solved compared to our CNN was to make it faster in terms of test time, because now we only have one CNN rather than having 2,000 CNNs before. So the next extension was the fast RCNN. So you might also think, why we are doing this multi-stage training? Why can't we use just one single neural network that could be able to do everything? So this is exactly the idea for fast RCNN. So what they did is, it is similar to SSP-net. So you have still SSP layer, but just one of the pooling. But then they solve the problem using these two additions. So they proposed a softmax layer at the end of the convolution layers. In parallel, also a linear regression layer, so that you can just train just one single CNN with all these. So it was better in terms of accuracy compared to RCNN and SSP-net. It has exactly the same kind of test time because you still use the one CNN. But one other problem is we're still using this select-to-search algorithm, which is not a neural network, but an external algorithm to actually find these proposals. So in the faster RCNN, they solve this problem using called regional proposal network. So now we are one step closer. So we have used CNN to extract the features. Why can't we use the same CNN for also to generate the proposals? This is the basic idea. So what they do is like at the end of the last convolution layer, there is a 3x3 sliding window that actually scans the whole feature map and make it into a lower dimensional space. For each of these points in the last layer, they proposed different regions based on these K anchor boxes of fixed size. So the 2K scores corresponds to the softmax probabilities for the K anchor boxes, and the 4K corresponds to the object location length with X and Y. So the goal of the RPN is to propose these objects, but should not actually classify them. So if any of these regions pass a threshold, it will be passed through as a proposal. And the rest of the layers are similar to like a fast RCNN. So you propose a ROI pooling layer, a classification layer, and a linear regression layer. So basically, faster RCNN you can think as like a regional proposal network for making the proposals, and then a fast RCNN network. And the further extension was to use the fully connected layers, fully convolution layers for the RFCN. The idea is, suppose if you want to detect, this is a face. If you could able to detect eyes, left eye, right eye, and a teeth or nose, you can say that is a face. So they want to use like a position-sensitive ROI maps to do this. So what they do in this case is, after the feature maps are passed to a convolution layer, which does this, does the position-sensitive score maps. And it is the size of K cross cross, K by K plus into C plus 1, where you have C classes, one for background. And each of these ROI layer is again passed to position-sensitive ROI pool, where you get like a K cross K times K kind of a array where you average and then you classify. So if you see that example, so here is an image and the ground truth, and then the regional proposal is the solid yellow box here. And then these 9 are the position-sensitive score maps that are corresponds to left, top to the bottom right, that case of a baby. And this solid yellow box here is corresponding sub-region of ROI. So you actually do the activation here. Suppose in this case, this box is activated for this position-sensitive score maps. So you find that's kind of high here. So you actually basically do the activation for each of these score maps. And then in this case, since it is kind of overlapped, you have like all of them kind of activated, and then you say that's, it's a boy. Whereas in this case, the rightmost, where the ROI is not kind of aligned, but the score maps are still the same, but then the subregions are now kind of displaced. So only in this column you see like there is kind of activations, but the other cases there is no. So since majority of the cases is not there, so you say like, it's not detected. So we have seen like the first class of object detections, where we use regional proposals and then try to detect. And the second class where you think this is like a unified framework. So one of the popular model in this case is YOLO, which means that you only look once. So basically what they do is, you have an image, you divide that image into like S cross S cells. For each cell, you kind of predict capital B bounding boxes, and you have like one confidence score per box. And irrespective of the number of these predicted boxes, each cell is only responsible to detect one object. And then each cell will also have like C-class probabilities. So YOLO network has like 24 convolution layers and 2 fully connected layers. So the output tensor at the end of the YOLO is 7 cross 7 by 30, because they have, I think it's 20 classes. And then in the case of walk dataset, they used a grid cell of 7 cross 7. So in this example, so these are all the predicted bounding boxes, but then you only select the one which is having the high probability, and these are the corresponding classes for those grid cells. I mean, this is one of the first, I would say, like a real-time object detection. You could process like 45 frames per second. And the second one is called SSD. The main problem in the YOLO case was because you have this constraint of having one cell could only able to detect one object. If there are many objects which are kind of very close together, it was not able to perform well. So they come up with a new architecture called single-shot multi-box detector. The basic idea is it could able to solve this problem by having anchor boxes of different aspect ratios and scales. These boxes are similar to the bounding boxes in the fast RCNN. So it uses there is no like a regional proposal here, but it uses the VGG16 for the feature maps. And then since there is no dedicated RPN, they uses the convolution filters for the object detection. And to be able to detect objects with the different scales, what they do is they actually fuse the predictions from different feature maps of different resolutions. So basically what they do is called multi-scale feature maps. Let me give you an example. So suppose we have an image. Yeah, here we have like a cat and a dog, and we have like here the 8 cross 8 feature maps, and then 4 cross 4 feature maps, and these are the anchor boxes of different scales and lengths. So if you see like this dog is kind of detected in 4x4 feature map, but not on any of these. But on the other hand, like cat is detected in 2 of these anchor boxes, but not in 4x4. So basically, like higher resolution feature maps are used for detecting smaller objects, and lower resolution feature maps are used for detecting bigger sizes of objects. So let's compare. Like we have seen like all of these. So basically, I mean, this is like the journey, I think, last 4 or 5 years from 2014 till 2016 or something. The first one was, SS corresponds to selective search, and RCNN was the first one. So all this comparison on work 07 test data set. So initially, these are the ones which actually give very good precision. But if you see, like, it is to take a long time for each image. So the frame per second is very low. And then comes the fast and fast RCNN. They have improved the accuracy, but then, still it's not so good in the case of speed. Finally, like we have the YOLO and the SSD. They're pretty fast. Like you still have good accuracy, but then they're kind of very good in the case of real-time object detection. So basic final conclusion is like regression-based models. I mean, can usually be processed in real time, but there's a slight drop in the accuracy compared to the region proposal methods. Yeah. How is it related to us? So as I said, like we are doing autonomous cars. So one of the important stuff you need to is to do the perception of the environment. So object detection is one of the key component of that. So these are like the results from our group. I mean, based on our own architecture of CNN and also tracking, but these are on the results from a public data set. And we are also in collaboration with road authorities. The basic goal there is to actually find the road debris, whether there's a pothole and road unevenness. So that helps them to actually do the road maintenance. And also for our self-driving cars, they know like it's detected, so they steer maneuver in a different way, try to avoid these road debris. Yeah, that's all. Thank you.